to have you here for First Principles Daily, episode 22. It's June 27th, 2026. Let's break something down to its raw materials and build the reasoning back up. Geothermal could supply steady power anywhere if the cost of reaching hot rock fell to the price of pipe and steel alone. A few kilometers down, the rock under most places on Earth already sits at temperatures that could drive a turbine without any fuel at all. Yet geothermal supplies only a tiny fraction of global electricity because the dominant expense is not heat, but the act of drilling and completing a well that can extract it reliably. The raw materials needed to line and seal such a well are modest. The finished project is not. That gap is the entire story. Geothermal development today follows the same pattern the oil and gas industry refined over decades. Operators locate a naturally permeable hot reservoir, drill a production well and an injection well, and hope the formation lets fluids circulate at useful rates. Most of the planet lacks those convenient conditions, so viable sites remain rare and geographically concentrated. Each well is treated as a one-off engineering project whose success is uncertain until the bit reaches depth. Drilling rigs, crews, mud systems, and casing are mobilized at oil field day rates. The risk of a dry or low-flow hole is carried entirely by the developer. Permitting timelines stretch because regulators review each location individually. Supply chains deliver custom-sized casing and cement on a per-well basis. Financing carries heavy risk premiums precisely because failure rates are high. The result is that capital cost dominates the economics. Once the wells are flowing, the marginal cost of the kilowatt hours is near zero. That structure feels normal inside the industry because every participant optimized around the same inherited constraints, rather than questioning whether the constraints themselves could be removed. The conventional approach also embeds assumptions about reservoir behavior that limit scale. In a typical hydrothermal project, the formation must already contain both heat and natural fractures or porosity, so that water can flow without additional stimulation. When those conditions are absent, operators must either abandon the site or attempt hydraulic fracturing, which adds further regulatory scrutiny and uncertainty about long-term flow rates. Surface equipment compounds the expense because each plant is sized and configured for the specific temperature and chemistry of the produced fluid. This requires custom heat exchangers, corrosion-resistant alloys, and turbine stages rather than standardized modules. Insurance and financing models treat the entire investment as a single high-variance bet. Lenders demand higher returns and shorter payback periods than they would for a repeatable manufacturing process. These layers of custom engineering and risk pricing reinforce one another. Fewer wells are drilled, learning stays slow, and unit costs remain elevated. A rough magic wand estimate begins with the physical minimum required to move heat from depth to surface. For a closed-loop system, that minimum includes steel casing or tubing to line the borehole, cement to seal it, a working fluid, and surface heat exchangers and turbines. Commodity prices for structural steel and cement are public. A several kilometer string of casing might contain on the order of a few hundred tons of steel, whose market value is measured in tens of thousands of dollars. Smaller quantities of cement and piping add commodity costs that are likewise modest. Adding the surface plant pushes the theoretical floor higher, but still leaves it dominated by manufactured hardware rather than fuel. Reported project costs for conventional geothermal plants today sit in the range of several $1 million per installed megawatt. Drilling and well completion form the largest single share. Dividing that finished cost by the commodity value of the steel, cement, and fluids yields an idiot index in the dozens to low hundreds, depending on the exact well design and location. The gap lives in three places. First, rig time. A deep hard rock well may require weeks or months of continuous operation at daily rates set by a market built for oil exploration. Second, the probability of success. Each well carries the full cost of mobilization, whether or not it produces commercial flow. Third, the bespoke nature of every installation. Casing diameters, cement recipes, and pump selections are engineered per site rather than standardized across hundreds of identical wells. Those three factors multiply one another, turning a hardware cost measured in tens of thousands of dollars into a project cost measured in millions. One way to see the arithmetic more clearly is to separate the variable and fixed elements. Suppose the steel and cement for a 3-kilometer well total roughly 150 tons of steel at a few $100s per ton, plus a few dozen tons of cement. The commodity subtotal remains well below $100,000 even before any discounting for bulk purchase. The surface power block adds another several $100,000 in materials when purchased at commodity or near commodity prices for steel, copper, and concrete. Yet the full installed cost per megawatt often reaches several $1,000,000. The difference arises because rig mobilization, crew wages, drilling fluid management, casing running services, cementing operations, logging, and contingency for stuck pipe or lost circulation each carry their own markups and waiting time charges. When a well is completed in half the expected time, the savings are real. When the same rig must be kept on standby for weeks because of regulatory holds or supply delays, those charges continue to accrue. Because most projects consist of only 1 or 2 wells, there is little opportunity to amortize learning or tooling across a production run the way an automotive or semiconductor line can. A from-scratch redesign would therefore attack drilling speed, repeatability, and risk first. Faster penetration in hard crystalline rock would require either new bit materials or entirely different energy delivery methods such as millimeter wave drilling or electric-powered downhole motors that do not rely on the weight-on-bit limitations of conventional rotary rigs. Repeatability would require shifting from custom well designs to factory-style casing strings and standardized wellheads that can be produced in volume rather than fabricated to order. Risk reduction would require either closed-loop architectures that do not depend on natural permeability or greatly improved subsurface imaging, so that dry hole probability falls before the rig is mobilized. Each of these moves demands its own enabling conditions. Sustained manufacturing scale for new drilling tools is one. Regulatory frameworks that treat standardized well designs as pre-approved once basic safety thresholds are met is another. Financing vehicles that spread dry hole risk across portfolios rather than single projects is a third. The genuinely hard parts are not physics, but the combination of rock mechanics at depth, the capital intensity of proving new drilling systems at scale, and the long permitting and insurance cycles that still treat every borehole as an experiment. None of these barriers is insoluble, yet none will fall simply because the heat itself is free. Objections about induced seismicity or long-term reservoir cooling deserve direct attention rather than dismissal. In enhanced geothermal systems, fluid injection can trigger microseismic events whose magnitude must stay below thresholds set by local regulators. Monitoring arrays and traffic light protocols already exist but add cost and operational constraints. Closed-loop designs that circulate fluid inside sealed pipes avoid pressure communication with the formation and therefore reduce that particular risk. Yet they introduce new challenges in maintaining thermal contact between the pipe wall and the surrounding rock over decades. Corrosion, scaling, and thermal fatigue of the tubulars become first-order concerns when the same steel string must operate continuously at elevated temperatures. Addressing these issues at the design stage through material selection, surface coatings, or periodic maintenance access would itself become part of the cost reduction pathway rather than an afterthought. When the energy itself carries no recurring cost, every remaining dollar traces back to the speed and repeatability with which humans can place and connect pipe in hot rock. The same logic that once made steel expensive until someone changed the furnace now applies to the act of drilling rather than to any consumable. The first visible signal that someone is treating geothermal drilling as a manufacturing problem rather than a geological lottery will be a published curve showing consistent well costs declining with the number of wells completed, not with the price of oil. Tomorrow and every day after, the show will examine one concrete example or one comparable opportunity. That's a wrap on today's First Principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own. I'm about to prove